An effective identification of microaneurysm in retinal eye using CONNET with ADAM optimization. Project partners are Kumudam, G. Divya Bharti, R. Divya Priya of Fields Institute of Science and Technology and Advanced Studies EC Department. Abstract. To diagnose the diabetic retinopathy, there is a necessity of finding the defects with a proper accuracy and with some advanced techniques to treat the disease as soon as possible before it reaching the severe stages. We were proposing a deep learning algorithm, CONNET, and ADAM optimizer to diagnose the diabetic retinopathy from digital fundus images and by using some data augmentation techniques which identifies the intricate features involved in the classification task of microaneurysms. We will collect some data sets from Kaggle and we will process the data sets in CONNET and ADAM optimizer to predict the defect and for the classification of microaneurysms with more accuracy and reduce in false positive. Objective. Our goal is to avoid a potential blindness through early detection and classify the microaneurysms. The seriousness of the disease can be assessed using a blood vessel segmentation and microaneurysm feature extraction. Introduction. What is diabetic retinopathy? A complication of diabetes that affects the eyes. Diabetic retinopathy is caused by damage to the blood vessels in the tissues at the back of the eye retina. So, the major risk of this problem is due to the poorly controlled blood sugar. What were all the symptoms of diabetic retinopathy? It includes flutters, blurriness, dark areas of vision, and difficulty perceiving colors. Spots may also occur, even blindness can happen. So, these and all caused due to the indulgent lifestyles, increasing life expectancy, were all the continuous rising of diabetic retinopathy. The stages of diabetic retinopathy were four, namely mild non-proliferative retinopathy, moderate, severe, and proliferative retinopathy. Is there any treatments can cure this disease? Yes, some treatments can help, but this condition can't be cured, and it requires a medical diagnosis as well as a continuous lab test or imaging is always required to diagnose this disease, and it can be a chronic disease too, which means it can exist for years or be a lifelong existing problem. By referring too many papers, we found early detection noise pixels occurring during the process of augmentation techniques is the most challenging task for the detection of microaneurysms. The false positive rate is also increased, which leads to the misclassification. Proposed method advantages. To overcome all these problems, we used CONNET with ADAM Optimizer. It is faster than other softwares to process the image and it is cost effective too. The consumption of time is also expected to be less and less film and other photographic equipment is used. And there is no need of processing or fixing chemicals to process the digital images. And the reduction of false positive and increase in accuracy has also been achieved successfully. This block diagram represents the methodology we used. The first block is the retinal input image. The second block is the pre-processing using histogram equalization. The third is also thresholding for segmentation. The fourth is convolutional net with ADAM optimizer to detect the microaneurysms and to classify the microaneurysm and non-microaneurysm. Methodology. The first step is to upload the input image in the program for the classification of microaneurysms and non-microaneurysms. Performing morphological operations is the second step, which subtracts and divides the least pixel values to range 0 to 1 for the normalization of the retinal image. The next step is to change the color of the input image by applying an adaptive histogram equalization and outsource thresholding method. Applying many filters like activation, dropout, dense, pooling, and convolution is performed in the next stage to create a feature map. An edge detection method is implemented in order to avoid noises in the image. And softmax layer is applied after the pre-processing for the binary classification of microaneurysms. Finally, an ADAM optimizer is used to enhance the accuracy. This slide represents the output of the extracted microaneurysms. This slide explains how microaneurysms is segmented in the previous slide. The first image is the retinal image. The second image is the conversion of original image to the grayscale image. The third image is the Ortho's thresholded image. Noises were removed using edge detection in the fourth stage. Finally, extracted the microaneurysms. This table represents the performance metrics of microaneurysms using standard convolutional neural network algorithm. The final accuracy we gained is 82.60% with an increased number of false positives. This table represents the performance metrics of microaneurysms using ConvNet and ADAM optimizer. The final accuracy we gained is 95.62% with a reduced number of false positive rate. This slide represents the performance metrics of false positive and accuracy using standard convolution, which illustrates that false positive is too high comparatively, the accuracy is too low. This slide represents the performance metrics of false positive and accuracy using ConvNet and ADAM optimization, which illustrates the false positive is decreased whereas accuracy is increased. Results. We have achieved a better accuracy of 95.62% and a proper classification of microaneurysms using ConvNet and ADAM optimizer. While comparing with standard convolutional neural network algorithm, ConvNet and ADAM optimizer gave more accuracy with less than false positive. Conclusion and future work. Detected and classified microaneurysms early with an increase in accuracy and decrease in false positive, which illustrates the misclassification is reduced using ConvNet and ADAM optimization technique. In future, we were planning to reduce the false negative rate and to classify the severity more accurately using our real-time images. These were all the references we referred to do our work. Thank you.